Hello everyone, welcome back to this online class. Today we are going to look at the Lagrange method of solution of partial differential equations, and in particular we are asked to find the integral surface of the differential equation given by x cubed p plus y in bracket 3x squared plus y q is equals to z times 2x squared plus y, where p is the partial derivative of z with respect to x, q is the partial derivative of z with respect to y. Now, the required curve should pass through the parabola x is equals to 1, z is equals to y squared plus y. So what we do here, remember this given equation is of the form, in general, that equation is of the form p times p small plus q times q is equals to r. And to solve it, we need to form the auxiliary equations. Auxiliary equation, or we call it subsidiary equation. It will be dx over p capital is equals to dy over q capital, which is equals to dz over r capital. So you need to solve this auxiliary equation or subsidiary equations to get two unique solutions, which we are calling the integral curves. So let's see. Our p capital is x cubed. So we are going to say put p capital is equals to x cubed. Our q is equals to y times 3x squared plus y. And our r is equals to z times 2x squared plus y. So when you make those substitutions, what are we going to get as our subsidiary equation? So we can say now, therefore, we need to solve dx over x cubed equal to dy over y into 3x squared plus y equal to dz over z into 2x squared plus y. So those are the equations that we need to solve to get two unique solutions. So in the first case, we call it case 1. In the first case, let me take the first two fractions, dx and dy. So we'll talk of dx over x cubed is equals to dy over y 3x squared plus, somebody might be asking, why have I taken the first two fractions? It's because in the first two fractions, we realize that the variable z is absent. So it is easy to solve them when we only have x and y, because z is absent in the first two fractions. So this is first order ODE. We need to classify it before we find the solution. Remember, this equation can be written as dy over dx is equals to y into 3x squared plus y divided by x cubed, which, if I open the bracket, it is the same as 3x squared y plus y squared over x cubed. And so this can also be written as 3x squared y over x cubed plus y squared over x cubed. And when you simplify, you're going to get 3 over x times y plus y squared over x cubed. And so we can now rearrange. So you can just say or dy over dx minus 3 over x times y is equals to y squared over x cubed. This is a Bernoulli's equation. This one is Bernoulli's equation. Bernoulli's equation. Remember, the general form of Bernoulli's ODE is that it is non-linear ODE, and we need to convert it to a linear ODE by making a certain substitution. So, how do we go about it? I need the function on the right-hand side to be purely a function of x only. So what I'll do, I'll divide the equation through by y squared. So when we divide by y squared, this is what you're going to get. This will imply that y raised to negative 2 times dy dx minus 3 over x times y raised to negative 1. Remember, we are dividing by y squared. So you apply the laws of indices here. And so on the right-hand side, you're going to get 1 over x cubed. 1 over x cubed. Now, we are transforming this equation to a linear ODE. Remember, it is non-linear because of the y squared on the right-hand side. So this y raised to negative 1, I am going to say let it be z. So let this be equal to z. So we say let z be equal to y raised to negative 1. So when you use chain rule, you'll find we need dz dx. Now that's the same as dz dy times dy dx. I'm using chain rule. And from here, you see we can be able to get dz dy. Dz dy is simply negative y raised to negative 2. So I'm going to replace it so that I get my dz dx. So this will be negative y raised to negative 2 times dy dx. So, or negative dz dy, no, negative dz dx is the same as positive y raised to negative 2 times dy dx. So that's a substitution which we are going to make, this one and also this. You see, we are replacing even the first term in that equation. So from here, we have found this is negative dz dx. And the other one is z. So therefore, this equation can now be written as, so you can say hence, we now have negative dz dx minus 3 over x times z is equals to 1 over x cubed. But you need to make the coefficient of dz dx to be equal to 1. So I'm going to multiply both sides by negative 1. So therefore, when you multiply by negative 1, we are going to get, remember this is what I'm doing, the whole of this equation, we multiply by negative 1. So we are going to get dz dx plus 3 over x times z is equals to negative 1 over x cubed. This one is now linear. It is linear ODE in the variable z as the dependent variable. So to solve a linear ODE, you need to find the integrating factor. So in this case, our integrating factor is equals to the exponential of the integral of 3 over x dx. You integrate the coefficient of z. If it were negative, you will have taken negative 3 over x. But in this case, it is positive 3 over x. So we just write positive 3 over x. Integrate that with respect to x. So when you integrate this, you're going to get exponential 3 ln x. Remember, when getting the integrating factor, don't write the constant of integration. So this can also be written as exponential ln x cubed. That is when you apply the third law of logarithms. And so this is equals to x raised to 3. So our integrating factor is x cubed. So let's multiply our equation. This equation, let us multiply it by our integrating factor. Let's see what you're going to get. So when you multiply by the integrating factor, we are going to get x cubed dz dx plus 3x squared, remember I've simplified, z is equals to negative 1. I have multiplied this equation by the integrating factor, which is x cubed. So look at the left-hand side. You see this can be grouped as a product. So this is the derivative with respect to x of the product of the dependent variable, which is z, and the integrating factor, which is x cubed. And so this should be able to give us negative 1. So you need to take note that every time, once you have multiplied a linear ODE by an integrating factor, the left-hand side must always be equal to derivative with respect to the independent variable of the product of dependent variable and the integrating factor. So that note is very, very important. So we now need to multiply both sides of this equation by dx to get this. So this implies that derivative of z times x cubed is equals to negative 1 times dx. And then now you integrate both sides. So we are going to get z x cubed is equals to negative x plus a constant c of integration, let's call it c1. But you need to replace z. Check where we defined our z. We said z is equals to y raised to negative 1, which is 1 over y. So replace z by 1 over y. So we are going to put z is equals to 1 over y to get this one, x cubed over y plus x is equals to c1. So this is our first integral curve, the first solution. You see from here, you could write c1 minus x is equals to x cubed over y, of which you could also make y the subject. Y is equals to x cubed over c1 minus x. So that is the first solution, our first integral curve. Let's look at how to find the second solution. That is case 2. So what will I do? I'll take this, the first fraction, equate it to the third fraction, and use my first solution to eliminate y, because I'm taking dx and dz. That means I need to eliminate y using the solution that I found. Remember, there are quite a number of methods of solving such kind of symmetric equations. Pick the method that will work for you. So we go for case 2. In case 2, this is what to write. So write case 2. In case 2, we have picked the first equation, which is dx over x cubed, the first fraction, and the last one, dz over z into 2x squared plus y. You see, I need to get rid of the variable y from these two equations, or from the equation, the OD that we have there. So look at our solution that we got from the first case. We said where there is y, we can put x cubed over c1 minus x. So we just write put y is equals to x cubed over c1 minus x. So this means that where we have 2x squared plus y will now be written as 2x squared plus x cubed over c1 minus x. That's what you have after replacing y. So how will this equation now look like? So therefore, we now talk of dx over x cubed is equals to dz over z into 2x squared plus x cubed over c1 minus x. And now this equation is a separable ODE. This one is separable ODE. Now, when you separate the variables, we are going to get, of course, I am cross multiplying this by 2x squared plus x cubed over z1 minus x. So we are going to get 2x squared plus x cubed over c1 minus x. And this, you are dividing this by x cubed. This is the coefficient of dx is equals to dz over z. So we have separated the variables. We need to simplify that equation before we integrate. So if you look at this equation, you realize that the term on the left-hand side is not easy to integrate unless we simplify it. So I'm going to divide by x cubed to get this. This can now be written as 2x squared over x cubed plus x cubed over x cubed into c1 minus x dx is equals to dz over z. And so you can simplify this further. You can write or 2 over x plus 1 over c1 minus x, this is dx, is equals to dz over z. Now it is easy to integrate both sides of this equation. So what are we going to get upon integration? This will give us the first one, 2 over x. When you integrate with respect to x, you'll get 2 ln x plus, when you integrate 1 over, remember c1 is a constant, so 1 over c1 minus x will give you negative ln c1 minus x. So I'll get rid of this plus, so let it be negative ln of c1 minus x. Remember, you can use substitution to integrate this. You get the same thing. On the right-hand side, we are going to get ln z. And then there must be a constant c of integration. Let's call it c2 plus ln c2. This solution can also be written as, when we apply laws of logarithms, we are going to get ln of x squared over c1 minus x is equals to ln c2 times z. And so when you take exponential on both sides, we are going to get x squared over c1 minus x is equals to C2 times Z. But now we need to get rid of C1 minus X. What is this equal to? Let's see our solution in the first case. C1 minus X, we got it here. It was equals to X cubed over Y. So we are going to replace that by X cubed over Y. So we say put C1 minus X to be equal to X cubed over Y. So upon substitution, we are going to get this X squared over X cubed over Y should be equal to C2Z, which you can also write as, when you simplify, is the same as X squared Y over X cubed is equals to C2Z, or the x's will cancel, so this Y over X is equals to C2Z. Or you could also make C2 the subject. If you make C2 the subject, what are we going to get? So you write, or Y over XZ is equals to C2. So this one is our second solution, or the second integral curve. Now we have the two integral curves. How do we find the integral surface? So let's see how to find the integral surface. So now integral surface. Remember, the integral surface has this general form that phi of C1, C2 should be equal to 0. So let's replace C1 and C2. Look at our C1 in the first solution. Our C1 was X cubed over Y plus X. So that's what I'll write in place of C1. So you can say, or phi of X cubed over Y plus X. Let me remove that bracket, comma. C2 is Y over XZ, and this should give us 0. And I told you, remember, phi here is an arbitrary function. If you factor out one of the parameters, let's say the second parameter, which is Y over XZ, this is also equals to an arbitrary function, call it phi1, of the first parameter, which is X cubed over Y plus X. So that's another way of writing that integral surface. But remember, there are some constraints that we have to apply to our surface. We are told the surface passes through the parabola. X is equals to 1 and Z is equals to Y squared plus Y. So put X is equals to 1. We are applying the condition. When X is equals to 1, what are we going to get? We are going to get Y over Z. Remember, we are substituting it here in this equation. This equation star, this one, let's call it star. This is the required integral surface as long as you know the arbitrary function phi1 of X cubed over Y plus X. That's what we need to determine. So we are going to apply those two conditions. The first one is that X is equals to 1. So when you put X is equals to 1, we are going to get Y over Z is equals to phi1 of 1 cubed is 1. So that's 1 over Y plus 1. Another one, you put Z is equals to, Z is equals to Y squared plus Y. In the same equation here, what are we going to get? We are going now to get Y over y squared plus y is equals to phi 1 of 1 over y plus 1, which you could also write this as, when you simplify the left-hand side, you get 1 over, look at the denominator, y is common, you could factor that out, so that we have y over y into y plus 1. And the two y's will cancel, so we have y, let me write everything. This is the same as y in the numerator. Denominator, we have y into y plus 1 is equals to phi 1 of 1 over y plus 1. So that's what we have. And now these two y's will cancel, this and this will cancel. So you can just say therefore 1 over y plus 1 is equals to phi 1 over 1 over y plus 1. So that's what we have. Now, remember, our task is to find phi 1 of x cubed over y plus x. But here we know phi 1 of 1 over y plus 1. So I'm going to let this parameter to be another variable, say w. So we are going to let, we can write here that, you see this parameter where we have 1 over y plus 1, let this be equal to w. So we can write let w be equal to 1 over y plus 1. So I need to make y the subject. So from here, we get 1 over y is equals to w minus 1. So therefore, where we have y, it will be equal to 1 over w minus 1. So therefore, what is this one in terms of w? So you can just say hence, where we have 1 over y plus 1, this is the same as 1, where there is y you put, we are going to put 1 over w minus 1. W minus 1, that is y, then plus 1. And so you can simplify this. When you simplify, this you can also write as 1 over, look at the denominator, I need the LCM in the denominator. So we'll have 1, here we'll have w minus 1, that's our LCM, then plus w minus 1. I'm combining these two into one fraction, which you can also write as 1 in the numerator, denominator, the 1 will cancel. You see the positive 1 and the negative 1 will cancel. So we have w over w minus 1, w over w minus 1. That's what we have, which you can write as w minus 1 over w. So we have found this in terms of w to be w minus 1 over w. So we are now saying that therefore phi 1 of w is now the same as w minus 1 over w. But what did we want in our solution? Look at our equation star. We wanted phi 1 of x cubed over y plus x. So where there is w, I'm going to replace that by x cubed over y plus x. So you say from here, if I put w is equals to x cubed over y plus x. What are we going to get? We are going to get phi1 of x cubed. Let me write in a better way. Phi1 of x cubed over y plus x. This will be equal to, in the numerator, we have x cubed over y plus x minus 1. That's the numerator, w minus 1, over w, which is x cubed over y plus x. If I multiply both numerator and denominator by y, let's multiply by y. That's a multiplication. Let it not confuse you. What I'm multiplying here is dot y, and even here times y, numerator and denominator. So what are we going to get? In the numerator, we are going to get x cubed plus xy minus y. In the denominator, we are going to get x cubed plus xy, which you can also write as, look at x is common in the numerator, so we can write this as x cubed plus xy minus y over x in the denominator, so that we have here x squared plus y. So we now know phi1 of x cubed over y plus x. And we said equation star is our required integral surface, as long as we know the arbitrary function phi1 of x cubed over y plus x. Now that we have found it, we are going to replace that in equation star. So you can say, therefore, equation star becomes, remember the left-hand side is y over xz. So you can say, hence, equation star becomes, hence, that should be hence equation star becomes, on the left hand side, what do we have? It is y over x z, y over x z, and on the right hand side now, instead of phi1 of x cubed over y plus x, we are going to write what we found here. So it should be now x cubed plus xy minus y, everything over x into x squared plus y. And you see the x will cancel with the other x. This one will cancel with this. So that when you cross multiply, simply this can now be written as y over z is equals to x cubed plus xz minus y over x squared plus y. Or you could also cross multiply to get y times x squared plus y is equals to z times x cubed plus x. Was it xy? This was not xz. There's a correction here. I don't know where we got the z from. Yet it should be y. So this should be y. We need to change it. I don't know where we got z from, so it's not z. So that's plus xy minus y. So what I've found here is the integral surface of the given differential equation, which passes through the parabola z is equals to y squared plus y and x is equals to 1. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech and you'll find me right there. Also, Don't forget to comment, like, and share this video. And meet next time we look at other problems in partial differential equations. Bye-bye.